Alright, let's work some gas law problems. In the previous section we talked about a few of the gas laws. Talked about Charles' law, talked about Boyle's law, and Gay-Lussac's law, and then we put them all together to form the combined gas law. I just want to work a few example problems that you may see on an exam coming up, or so just some things to refresh your memory. Alright, so the first problem reads, a gas occupies 100 milliliters at 150 kilopascals. Find its volume at 200 kilopascals. Well, first of all, we need to figure out what we are given. Okay, our initial volume is 100 milliliters. Our initial pressure is 150 kilopascals. We're looking for the second volume, and we have a final pressure of 200 kilopascals. All right. Since we're dealing with pressure and volume, we know that we must be working with Boyle's law. Boyle's law. Okay, and remember when Boyle's law, or according to Boyle's law, as pressure increases, volume decreases. So as we increase the pressure to something, volume decreases. Think of the Coke can. If you increase the pressure on the outside of it, it's going to squish down to where the volume that it will hold decreases. All right. So let's work. We're going to use our combined gas law. That's the easiest way to remember. That's one of the 2 or 3 formulas that you're going to have to remember in this chapter. The combined gas law. Okay, so how do we use the combined gas law? We don't have a temperature present. Well, if we do not have something present that's in our combined gas law, we can simply ignore it. So our formula would be P1V1 equals P2V2. Now we simply plug all of the numbers in, perform the basic algebra 1 or arithmetic calculations on it, multiply 150 times 100, divide by 200, and we end up with 75.0 milliliters. Why 75.0? Well, we must remember significant figures. Significant figures. Alright, second problem. A gas occupies 473 cubic centimeters at 36 degrees Celsius. Find its volume at 94 degrees Celsius. Alright, so let's look at what we're given. We're given the first volume of 473 cubic centimeters. You should remember that cubic centimeters is a volume measurement. Remember, volume is length times width times height. Our initial temperature measurement is 36 degrees Celsius, which we know we must convert to Kelvin. Our final volume is what we're looking for, and our final temperature is 94 degrees Celsius, which we know we must convert into Kelvin. Just a quick reminder on how to convert to Kelvin. We simply add 273 to the Celsius measurement. Now, since we're dealing with volume and temperature, we know that we're working with Charles' law. Charles' law. And Charles says that as temperature increases, volume also increases. So let's plug this into our formula. Alright, we are not working with pressure, so we can ignore pressure. So our formula is V1T2 equals V2T1. We simply plug these numbers in to our formula that we get from our given box. 473 cubic centimeters times 376 Kelvin divided by 309 Kelvin. Obviously the Kelvin temperatures, the Kelvin units cancel. We end up with cubic centimeters as our units. And that's going to be 562 cubic centimeters. 562 cubic centimeters. Remember, cubic centimeters is a volume measurement. Alright, our third example problem. A gas pressure is 765 torr at 23 degrees Celsius. At what temperature will the pressure be at 560 torr? Alright, so let's look at what we're given. Our initial pressure is 765 torr. Our initial temperature is 23 degrees Celsius. Remember, we must convert to Kelvin by adding 273. Our final pressure is 560 torr, and our final temperature is what we are looking for. So if we're dealing with pressure and temperature, we know that we must be dealing with Gay-Lussac's law. Gay-Lussac's law. Gay-Lussac says that as pressure decreases, since we have a pressure decrease here, temperature must also be decreasing. Temperature must also be decreasing. Remember, these two values are directly related. Alright, so let's look at what our work. Alright, since we're not working with volume, we can simply ignore it. And we just plug into our formula and calculate it with our calculator. Alright, 560 times 296 divided by 765 gives us negative 56 degrees Celsius if we work that math, or 217 degrees Kelvin. Now, one last problem. I want to work with the combined gas law. Alright, the problem reads, a gas occupies 784 cubic centimeters at 71.8 kilopascals and 25 degrees Celsius. Find its volume at STP. We need to remember what STP is. Remember, the temperature value at STP is either 0 degrees Celsius or 273 degrees Kelvin. And our pressure measurements either going to be 1 atmosphere or 101.325 kilopascals. So let's look at what we are given. Our initial volume is 7.84 cubic centimeters. Our initial pressure is 71.8 kilopascals. And our initial temperature is 25 degrees Celsius, which we remember we must convert to Kelvin by adding 273. Our volume is what we're looking for. Our final pressure is 101.325. Remember, it's probably going to be easier to use the same pressure measurements or the same pressure units as we had initially, rather than convert in this case. And our initial temperature is 273 degrees Kelvin. Remember, use the same units. We must use the same units. We may have to make a conversion in order to use the same units. This is the combined gas law, so as pressure increases and temperature decreases, we know that volume will also decrease. So let's look at our work. We start off with the PVT equals PVT equation that we need to memorize, and just plug all of this information in. So our initial pressure, our initial volume, and our final temperature all multiplied together. Then we're going to divide it by our final pressure and our initial temperature, so that we can isolate our final volume by itself, and we should end up with 0.09 cubic centimeters. 5.09 cubic centimeters. Remember 3 sig figs, because that's what we have everywhere. It's 3 sig figs. And that concludes the problems.